on here. So note that in this one here, on the x-axis is plotted the reaction coordinate. This is another way of saying this is the progress of the reaction. So as the reaction goes from the reactants to products, that's the reaction coordinate. On the y-axis, energy. This horizontal line here on the left represents the energy of the reactants. This horizontal line here represents the energy of the products. Okay? Note that in this diagram, the energy of the reactants is higher than the energy of the products. In this one here, it's the reverse. The energy of the reactants is lower than the energy of the products. So, which reaction energy diagram represents the wood-burning reaction? Is it this one or is it that one? Okay. So I didn't put any letters or numbers, so okay, is it this one or that one?
That one. This one.
This one.
This one.
Okay, so again, we know that the wood-burning reaction is exothermic. So does this wood-burning reaction is represented by this reaction energy diagram or that reaction? Who says it's this one? And who says it's that one? Okay, so those of you who said this one are correct. Okay, so it's this one, which represents the exothermic reaction. So for an exothermic reaction, the energy of the products is lower than the energy of the reactants. Okay, so let me write this down also on the chalkboard, because there's some terms which we can use to help us with this idea. So we have energy plotted here, and the reaction coordinate. Okay, so this is the energy of the reactants, and this is the energy of the products. So note that in this case here, this is higher energy, and this one is lower energy. Now, which energy state is more stable, the high energy state or the low energy state? Yes, so the low energy state, this means more stable. And this means less stable. Okay, or another way of saying this is going to be stable, or this will be unstable. So as all of you know, since you're in college now, you do your things over the weekends, you know, you have fun and go out. You probably want to be around, in general, stable people as opposed to unstable ones. And the reason for that is because it is a higher energy substance. Is it more reactive or less reactive? Okay, so which one's more reactive? The higher energy, less stable, unstable, or is it going to be the lower energy, more stable, or stable ones? Okay, so which one's more reactive? Yeah, so this is going to be more reactive. More reactive, and this one is less reactive. Okay, now also showed here, what is this difference in energy called? Okay, because note that we have, so what's that difference in energy called there? Okay, because note that here, we're showing that the energy of the products is lower than the energy of the reactants. And in Chem1B, how do we quantify that energy is called heat of something? Heat of
dissolution?
Yeah, that heat, dissolution type of reaction is, we call it heat of reaction, or delta H. Okay, so that's delta H. And note that in this case, is delta H greater than 0 or less than 0? Okay, because the products are lower energy than the reactants, delta H is going to be less than 0. Okay, so again, less than 0, this means it's exothermic. Okay, now the other thing that textbooks like to do is note that the reactants are going in this downhill direction. And that's what chemical reactions like to do. They like to go in those downhill directions. So it's just like, you know, if you have a ball here, you know, ball will roll downhill. So if you have like a endothermic reaction, okay, these are our reactants, and this is our products. Note that this is uphill. And, you know, balls don't like going don't naturally go in that uphill direction unless you apply some energy to that. So again, we can use this reaction going in this downhill direction as the reason that most reactions are going to be exothermic. So again, balls don't roll uphill all by themselves. However, they will roll downhill all by themselves. Okay, let's go on the next slide. Okay, so here's some examples of reactions. We looked at the word-burning reaction. Is this reaction fast or slow? Yeah, this is actually a pretty fast reaction. Are any of these other reactions fast? Yes, this is a fast reaction. Is grass growing fast or slow? Yes, slow.
Mr. Yee, why is grass growing exothermic?
No, I'm not saying it's exothermic. I'm just saying it's fast or slow. Okay, so again, this is the difference between kinetics and thermodynamics. Thermodynamics doesn't tell us whether a reaction is fast or slow. It just tells us whether energy is released or energy is absorbed. Okay. For kinetics, that tells us whether a reaction is fast or slow. Okay, so again, graph's growing. This is a slow reaction. How about iron rusting, fast or slow? Yeah, that's a slow reaction. And how about diamond turning into graphite? Is that fast or slow? Slow. That's very slow. Okay, so we can use kinetics or reaction rates to describe how fast or slow these reactions are. And the other thing we can do is we can control how fast these reactions are. So, for example, you know, as college students, we got to make sure we make our dollars go as far as we can. So I'm not sure if you do this as a college. I did this when I was a college. If my bread went moldy, I would just pick off all the moldy part and eat the rest. You don't want to throw that money away there. Okay, so you got to control that food spoiler somehow. And we can use reaction rate to control how fast food spoils. If you don't have enough money to buy a car with leather seats, then they'll have the vinyl seats. And if you have it long enough, you'll see those seat covers crack. Okay, control the rate of that reaction too. And then the other thing too is if there's concrete and it takes some period of time to set that concrete, and we got to make sure that it's set properly. So that's another example of reaction rates. I'm not sure if you can see this picture. This is a guy with a very dark, deep tan or sunburn here. Okay, and if we know that if a person is exposed to too much ozone, too much UV radiation because our ozone layer has been destroyed, That's going to cause sunburn. And note that the destruction of the ozone is another example of chemical reaction rates of kinetic. So there's ways to control all these different chemical reactions. We'll learn how to do that in this next section. Okay, so again, we said that atoms and molecules collide sufficient energy with the correct orientation for bonds to break and form. The three factors are temperature, concentration, and the catalyst. Now, of these three factors, which factor increases the energy of the reaction? Okay, so I'm going to erase this part here. I'll represent these reactants by, let's put these little circles here. So this is going to be our reaction container. We have these are our reactant molecules. So which of those three factors, temperature, concentration, and catalyst, increases the energy of the reaction? Okay, so maybe what we can do is define, just review what these, okay, so what is the definition of temperature? Yeah, so like Juan says, this is a measure of the average kinetic energy of a molecule. Okay, so this measure of the average kinetic energy of a substance. What does kinetic energy measure? Yeah, how fast or how slow a substance is moving. Okay, so really, this measures temperatures. Again, you can also say that's a measure of how fast or how slow the molecules or atoms of the substance are moving. Okay, for concentration, what is the definition of concentration? It's a ratio of, yes, it's a ratio of something. Yeah, so for molarity, it's the moles of